imagine you are playing a game with your friend. Okay, you are standing still and your friend is walking around you in a circle. And you are always facing your friend. So you are turning as your friend is walking around with you. Now, if the friend now throws a ball at you, what is the path of the ball that you will see? Just think about this. Will you see a straight line? Will you see a curved path? Will you see a straight line towards you or at an angle? Now, this is something that we will analyze today, but this is something that you can try at home. Now, let me switch the roles. What if you were walking around your friend and your friend was at the center, still facing you all the time, you are walking around in a circle, and the friend throws a ball at you. Now, will it be different? Will you see the same path or will you see a different path? So, we will talk about kinematics today and we will help answer some of these questions in this session. This is a refresher capsule on basic concepts. A couple of disclaimer points though. This session is really meant to serve as a refresher and just show the spirit of the derivations. These derivations are often not very rigorous, so don't be under a false sense of security that you have understood the concepts in detail. You really have to work it out yourself later on to really master these concepts. You also need a lot of practice, lot of experience applying these concepts in different situations, in different problems for you to really understand how to use them. You know, these are simple equations, but they are great weapons. You need to understand how to use them. Right? So, that is another very important point. And the third point that I want to make is whenever you are stuck in a complex problem, always try to go back to basic fundamentals, basic first principles. And I found that to serve me quite well, and I hope that will serve you well, rather than try to remember a lot of different equations. Now, let us consider a vector R. And let us say there is a unit vector along the direction of r, let me call it er hat. Now, for the notations used in this capsule, go back and look at the previous capsule where I talk about the notation that we will use. Now, let us say r is a vector which has magnitude scalar r along the direction er hat. And let us say this is a vector with constant magnitude but changing direction. So, a small time instant later, let us say the vector r still has the same magnitude but has a different direction. Now, again when you go back and look at the convention, you will realize that the vector physically being in a different place does not matter. So, I might as well draw it starting from the same point. So, this is like my r old and this is like my r new. So, my change in vector over that small time instant is delta r, and let us say this is happening over a time instant of delta t, and let us say the rate of rotation of this vector, because it is changing direction, that is omega. Now, if I were to figure out what is the derivative of this vector, remember vector has magnitude and direction. Even if the magnitude is constant, if the direction is changing, it will have a non-zero derivative, right? So, this would simply be limit as delta t tends to 0, delta r over delta t, and delta r, as you can see, is a vector for a very small time instant. It is a vector that is perpendicular to the original r. Right. Now, if I set up another unit vector, let me just call it E theta hat, which is perpendicular to ER hat. I could have drawn it right here, but I have drawn it here. Then delta r as a vector is really radius times angle, right. So, this angle is omega times delta t, because in delta t it would cover that much angle. And this radius is r, so this would give me limit as delta t tends to 0, r omega delta t divided by delta t in the E theta hat direction, right. So, I would get delta t cancels out, I would get r omega e theta hat. More generally, as I said, this is a crude derivation, but more generally, you can now start to see this is nothing but a cross product of omega and r. Now, this is a fundamental expression that is used in all of kinematics. Now, this is only valid when you are talking about a vector that has constant magnitude. The derivative is only due to the change in orientation of the vector, and this omega is nothing but the angular velocity with which this vector is changing direction. Okay. Now, if I go back to a situation where r could also be changing magnitude, then I would have two terms. Just using the product rule, I would get an r dot still in the old direction, which this is the term due to change in magnitude, plus I would get still a term due to change in direction. That would be the second term. So, this would be the more general expression for a derivative of a vector, but in most cases we will be dealing with constant magnitude, so we will only have this particular term. Okay, now let's take this forward and use this to develop kinematics equations. First, let me consider an origin O and let's say 2 points A and B. So, I have the position vector of A, position vector of B, and I have this position vector of B relative to A. So, I can write RB is equal to RA plus RB with respect to A. Now, this is just a vector addition. There are no assumptions involved in writing this, but I can differentiate this once and I get VB is equal to VA, where the V's are now velocities, and the velocity of B relative to A, and I can do this once more and I get acceleration of B is equal to acceleration of A plus acceleration of B with respect to A. Now, this is again valid universally, no assumptions involved. However, now we can start making the assumption of the distance between A and B is constant or fixed. Or in other words, when we are talking about a rigid body, A and B are 2 points. If they are 2 points fixed on one rigid body, then the distance between both of them will be constant. So, what we are developing here is applicable to rigid bodies. So, example, rigid body. So, if A and B are 2 points fixed in a rigid body, then we get VB is equal to VA, and this relative velocity, because this magnitude is constant, distance is not changing, you would get what we derived earlier for a derivative of a vector with a constant magnitude. Here, omega is the angular velocity of the rigid body. Now, remember, velocity is always of a point, angular velocity is of a body or of a frame, right? You don't write angular velocity of a point, that would be wrong. Now, I can differentiate this again and I would get acceleration is equal to acceleration of A. Here, I can again use product rule where I will get derivative of the first term cross with the second term plus the first term cross with the derivative of the second term. So, I would get alpha cross RB with respect to A plus omega cross RB with respect to A. What I did is derivative of this guy is again omega cross that guy because it has constant magnitude. Now, here alpha is simply the derivative of omega, which is the angular acceleration, and this term is 0 because omega cross omega is 0. No, I am joking. This term is not 0. Please remember this. People often make this mistake. The order of the cross products is important here. This bracket is important here. So it's an omega cross r. That whole thing, you have omega cross that term. So this term is not 0. And in fact, many of you will recognize some of these terms because you might have seen them in different contexts. This is a very, very general expression. It is always applicable whenever the distance between A and B is fixed, is constant. So any rigid body, 2 points fixed on a rigid body, both these equations are applicable. And many of you will recognize this as the tangential acceleration alpha r, and this you would recognize as the centripetal acceleration. And you can quickly work out in the planar case, omega is always pointing out of the board or into the board. And then when you work out this cross product, you will see that this whole term is in the negative direction of the r vector. So it is pointing towards the center, so to speak, or in this case, pointing towards A. So tangential centripetal acceleration. So the fun part here is that we only needed to use an expression for the derivative of a vector with changing direction but with constant magnitude over and over again to derive these equations, which are now very general. And derivatives are always easy to handle. They are just product rules that you apply over and over again, unlike integrals, which are much harder. Now, the other interesting thing is if you go back and try to trace out when kinematics equations were first developed, it's of course a long history, but it seems Galileo was one of the first people to derive a formal expression for one of the kinematics relationships. So he derived S is equal to half gt squared, which is now very well known special situation equation. But Galileo was not the first person to be studying motion. That has been motion of heavenly bodies, motion of objects have been studied for thousands of years, starting from Aristotle, Archimedes, 200 BC, 300 BC. By the way, Aristotle and Archimedes are better known for some of their other works. Of course, everybody knows about the Eureka moment of Archimedes. By the way, there's one fun fact there. So King Herod II asked Archimedes to verify whether his crown was made of pure gold or not. All the sketches I've seen, all the images I've seen of Archimedes running out of the bathtub or running out of the bath shouting Eureka have shown Aristotle with gray hair and long beard. But when you go back and check the dates, it seems Archimedes was quite young, perhaps 21, 22-year-old. I don't remember the exact age, but go back and check that. So all the images that you see are wrong. Archimedes was much younger when he ran out and shouted Eureka. Anyway, so coming back here, okay, now let's take this to a more general situation of what if B is moving away or towards A. So they are now no longer 2 points with a fixed distance in between, but there is motion towards or away from A. Now let's define this new velocity. This is this relative velocity of B as seen from a rotating frame. And when I say rotating frame, the way to imagine it is, supposing there is a link and there is a sleeve that is sliding over it. Now this link you can think of as the rotating frame, and AB, now B is moving away from A, and that rate at which it is moving further away relative to this link is what is this velocity. Now on top of this, this whole link can be rotating, but that part of the velocity is not what I'm worried about here. Now supposing I have this, then I would have an addition to this equation where on top of this, on top of what I had earlier, I would have also this additional velocity superimposed. So I would have velocity of B as seen from the rotating frame. Now this will be the expression for velocity of B, because it will have the first two terms plus that relative velocity. Now if we differentiate this once more, then we would get acceleration of B is equal to acceleration of A plus the same thing as earlier, which is alpha cross R B with respect to A plus omega cross R B with respect to A. But remember, now in the derivative of this guy, you not only have this, because this was only valid when the distance between A and B is constant. When this vector had constant magnitude, that's when you had derivative of this vector was just omega cross this. Now you would have another term which is really coming from here, right? So you would also have omega cross VB as seen from F. So essentially, when I take derivative of this term, derivative of first guy cross with the second guy, that is here. First guy cross with derivative of second guy now has two terms, that's why you get this. Plus, now we still have to differentiate this. Plus, again that derivative will have two terms, one due to change in magnitude, which will just be acceleration as seen from the rotating frame, plus a term due to change in direction, which is omega cross VBF. Now, as you can see, there are two identical terms here. So you can consolidate this and write this as acceleration of B is equal to acceleration of A plus alpha cross R B with respect to A plus omega cross R B with respect to A plus acceleration of B relative to the rotating frame plus 2 omega cross VB with respect to F. Now this is the most general form of the kinematic equation for acceleration. This you can apply anywhere. Here no assumptions are involved about A and B. They could be any 2 points. However, the difficulty is really to apply them, to apply these two equations. You really have to figure out how to set up your frames, how to, what are your angular velocities, how to choose your points, how to choose your unit vectors. That is where as I was saying, practice and experience helps a lot. So this is, like Lord of the Rings. This is like one ring to conquer all the rings, but that doesn't mean you can wield that ring. Right, that ring can corrupt you. No, I'm joking, but it's a tough equation to handle. Right, it's easy to derive, but to actually apply, you need to practice again and again and apply this many different ways. Even on the same problem, you can apply the same equation many different ways, depending on what is your choice of origin, unit vectors, reference frame, rotating frames. How do you split your problem into multiple steps, and so on and so forth. Okay, once we have derived this equation, what is also interesting, you guys might have already noticed, is this curious term here, which is 2 omega cross with VBF. And many of you may recognize that as the Coriolis term. Yes, that is indeed the Coriolis acceleration. And there's a lot of debate about that. You will see lots of examples online, a lot of discussions online. There's this talk about toilet bowl. The way it flushes, the way it will rotate one way in the northern hemisphere, another way in the southern hemisphere. Again, there are a lot of interesting videos that I will encourage you to go watch. And I was thinking, if I ever get a chance to travel to the southern hemisphere, I will observe, I will take videos of how the toilet bowl flushes. But sadly, I visited a couple of years ago, but at that time I completely forgot to shoot videos of the toilet bowl. But anyway, I think something more interesting would be cyclones, and again you guys are aware of the discussion in cyclones. But you will see this in all sorts of other situations. If you are talking about a crane where the crane is raising the boom, but at the same time the crane is also rotating. So both these motions happen together, and at the same time, let's say it's a telescopic boom, so it's extending outward while that whole motion is happening, right? So then you can clearly imagine that extending outward, clearly falls under this category where that's a motion relative to the frame, and then that ends up giving you a Coriolis term there. So there are lots of different interesting examples. You can even construct home experiments to test that out. So I would encourage you to go look at all of that. Okay, so coming back to these basic kinematic equations, in fact, these two are all you need in kinematics, and everything can be thought of as a special case of this. Even things we have studied like cylindrical coordinates, spherical coordinates, you don't really need to remember any of those equations. As long as you know how to set up frames and unit vectors, you can go back and use these same equations, and you should be okay with that. Now, even when you are talking about 2 points fixed on a rigid body, again remember, you can use that even if it's a fictitious rigid body. It doesn't have to be a physical rigid body. For example, you can go back to the first question I asked you about what if your friend is throwing a ball at you while walking around you, right? And that I like to, that's the famous Yogesh problem. You can try it at home, and it is easy to imagine now, after having seen this, that you will get a Coriolis term. Just like we were talking about, this is a tangential acceleration, this is a centripetal acceleration. This you can see right away that this is, since it's a cross product, this is always perpendicular to this relative velocity, right? So you can imagine a rigid body between you and your friend when the friend is walking around you, and when they are throwing the ball at you, that is this velocity over here, and that you will have a perpendicular component because of this Coriolis term. So you might see a bit of curving, again something for you to test at home. So with that, I leave you with the Gyan of the day and one final remark. So Gyan of the day is just like Archimedes, figured out how to solve the problem while he was taking a bath. You might have heard about, benzene was discovered when, not benzene was discovered, the ring structure of benzene was discovered when the discoverer was sleeping, and in their dream they thought that up. You might have heard about Newton sitting under a tree and then seeing an apple fall. Of course, that's also highly debated whether that really happened that way. But you can see in all these situations that people come up with great ideas when they are doing something else, right? So the Gyan of the day is, of course, spend a lot of time thinking about the challenges at hand, but also give yourself free time. Let your mind wander, and that's when the best ideas will probably click you. And the final remark is, remember again that you can learn anything on your own, no matter how limited the resources. I have a cousin who has learned swimming just by looking at YouTube videos. So everything is available online. All you need is little bit of patience and little bit of commitment. All the best.